Hello my friends and welcome back to the You Can Do TV channel.
Steel rotation sets the stage as prime turning takes over. The process flows seamlessly, with each tool taking its turn to cut with speed and precision. Depth and feed adjust smoothly, maintaining control while driving power into every move. The sequence feels strong, efficient, and unstoppable, a clear display of what prime turning can achieve. At WMTS 2015, the Citizen Syncom L32XII made its US debut, drawing attention with advanced multi-axis capability. The machine's setup immediately impresses, promising complex work in one cycle. The highlight is an 8-position B-axis, with 4 front and 4 rear stations, offering 135 degrees range of motion for angled machining. Supporting this, the Y2 axis expands flexibility, giving 9 positions on the back tool post, including 4 live and 5 static tools. Such configuration feels dynamic, opening new paths for part production. Together, these systems reduce setups while enabling turning, milling, and drilling in sequence. The demonstration shows smooth coordination, keeping every cut efficient and strong. The SORALUCE FMT 4000 opens with a striking capability: machining, turning, and grinding combined in one system. Its enormous workspace, offering 5-side access with an integrated rotary table, allows operators to handle large, high-strength materials with confidence. At the first stage, heavy stock removal and rough machining are carried out at 2 stations, supported by high feed rates and deep cutting. The next step demonstrates drilling with torque up to 900 Newton meters, as well as threading with oversized tools. These operations highlight the strength and stability of the drive system. Thanks to a swiveling milling head, even the rear side of the component becomes accessible. Then, pocket milling and finishing can proceed seamlessly, with the rotary table and tool change system ensuring uninterrupted flow. It is fascinating how multiple tasks are accomplished in a single setup without repositioning the workpiece. Circular milling and angled drilling add flexibility to complex parts. The ability to handle slanted surfaces is a notable technical advantage. Later, carousel turning is performed with diameters up to 1,800 millimeters on a powerful rotary table. Grinding completes the cycle, making the FMT 4000 a true all-in-one machining center. This versatility reduces handling time and raises efficiency across the workshop. Interrupted turning pushes Coroturn Prime B inserts through demanding cuts, exposing tool strength, chip control, and durability under stress. A robot tool changer manages a magazine of 130 tools, allowing non-stop transitions during demanding work. The stepless universal head adds adaptability, rotating for complex geometries without repositioning the part. A rotary traveling table, measuring 3,500 by 3,000 millimeters, supports components weighing up to 60 tons. The automatic head changing system integrates seamlessly, enabling the horizontal head of 230 millimeters diameter and 480 millimeters length to engage with external cooling. Such scale makes every stage look powerful and highly controlled. The Dodeca Mini KCPK30 cutter, with 40 millimeters diameter, removes material at AP 3.5 millimeters and AE 38 millimeters. A Rodeka alternative at 50 mm works with AP 2.5 mm. The general-purpose end mill KCPM 1516 mm adapts for AP 0.5 to 2 mm. Further steps include Harvey 2 cutters in multiple sizes, each optimized for depth and width. Every transition highlights both consistency and technical balance. Powerful bar stock machining takes center stage as the Index MS40C reveals its modular design. With up to 12 CNC cross slides, every movement is synchronized for maximum output. The V-shaped tool carriers grant access to both external and internal operations, fixed or driven. High-speed synchronous spindles with C-axis control ensure adaptability. Backworking adds 6 to 12 tools. The coordination on display underscores how complex production flows become streamlined into remarkable efficiency. Metal blocks are shaped with remarkable speed as high-performance trochoidal milling unfolds on the shop floor. Every rotation of the tool shows how efficiency and stability can be balanced when machining steel rated at 800 megapascals tensile strength. The cutting action gives an almost hypnotic sense of rhythm as the chips curl away. The sequence opens with roughing cuts on material 1.7225, using the NX RNVD pages 15368.450 tool. With a diameter of 10 millimeters and 4 flutes, it runs at 6,366 revolutions per minute. Feed rate reaches 2,546 millimeters per minute, with a cutting depth of 15 millimeters and step over of 4. At this moment, you can almost hear the strength of the spindle working under load. The second stage continues with another roughing operation, this time switching to the NX RNV pages 15326.450 tool. Diameter and flute count remain the same, but spindle speed drops to 5,730 revolutions per minute. Feed rate is adjusted to 1604 millimeters per minute, still holding 15 millimeters depth and 4 millimeters width of cut. The adjustment reflects how parameters are tuned to balance tool life and material removal. For finishing, the same RNV tool operates at a higher cutting speed of 230 meters per minute. The spindle rises to 7,321 revolutions per minute, while feed slows to 1025 millimeters per minute. Depth is reduced to just 0.1 millimeter, maintaining a 4 millimeter step over. Such fine finishing creates surfaces that are both accurate and smooth. The sequence of steps demonstrates both power and finesse in machining. High-feed milling begins with Ken Feed 2X, new 32mm tool on 42 CRMO4 steel. Speed reaches 2,500 revolutions per minute, feed 11,250 millimeters per minute, cutting 1 millimeter depth and 18 millimeters width. Energy rises as the R150 machine demonstrates its forming power on a number 24 aluminum pot. The blank disc is centered and clamped against the mold. With constant rotation, forming tools press firmly against the surface, stretching the disc outward. Each pass gradually defines the curve. The once flat sheet becomes a deep, durable vessel ready for kitchen use. A plain silver disc takes its first transformation on the lathe, where rotation and pressure awaken the foot of the goblet. A0925 sterling silver disc is mounted securely on the lathe. As the spindle rotates, a forming tool presses steadily, coaxing the flat blank into a flared contour. The shine of the metal at this stage feels almost alive. Each pass refines the profile, creating strength while maintaining elegance. The joining process reveals the harmony between form and craft. When the base form is finished, it is removed and set aside. Finally, a decorative ring is attached to the base, uniting all parts into a single gleaming goblet. How does a flat aluminum disc evolve into a shining bell ornament for the holidays? The process begins with a spinning lathe where the blank is centered and clamped firmly. Rotation brings stability, while the forming tool guides the metal against a solid mold. The sound of contact between tool and metal rings steadily, echoing through the workshop. Next, the operator presses the disc gradually, shaping it into a curved wall that will soon define the bell's profile. The smooth flow of aluminum against the mandrel ensures the contour is accurate. At this point, every adjustment reflects skill passed through years of practice. As the wall deepens, the base of the bell emerges, holding its round form without cracks or thinning. Tool pressure is increased where structure needs strength, and reduced where delicacy is required. Watching the edges fold neatly into place is unexpectedly satisfying. A moment of silence follows each pass, marking the operator's focus and patience. Finally, the bell is released from the mold, revealing a bright, seamless ornament. Follow the copper sheet as it transforms step by step into the body of a traditional ibrick, a copper coffee pot. The process begins with cutting the sheet to size and folding the edges inward to form a neat border. This early step prepares the material with strength and a defined outline. Next, the piece is placed on a hand-forming support rather than a lathe. The artisan presses and bends the copper gradually, shaping the round body. The rim is reinforced further with careful folding. Then, hammer blows are used to emboss vertical ridges along the body, adding both decoration and strength. Handles are shaped separately and fixed to the vessel. The craftsman reheats the copper with fire to restore ductility and even out the surface color. A liquid solution is brushed over the surface, protecting the copper. Finally, polishing reveals a brilliant shine across the surface, completing the transformation from flat sheet to cooking pot. Every trumpet carries not only sound, but also the heritage of design and craft. Inside the Vincent Bach facility, raw brass tubes and sheets arrive, waiting to be shaped into resonant instruments. The journey opens with bell production. Sheets are cut, shaped, and hammered into cones that will define the instrument's voice. Edges are filed and smoothed to remove irregularities, allowing the bell to vibrate freely without distortion. It is impressive how flat material gradually forms a resonant bell, foreshadowing the brilliance of sound it will produce. Next, lead pipes are prepared. Cylindrical tubes are drawn and polished, their alignment critical to airflow and tonal consistency. Each tube is measured multiple times to ensure a perfect fit with the bell and valve. Explore the intricate craft behind every handcrafted copper lantern. The journey begins with flat copper sheets, which are cut into precise shapes. Each piece is measured and trimmed carefully to ensure it will fit seamlessly with the others. These segments are then arranged to form the lantern's key sections: the pointed pyramid top, the side panels with their graceful openings, and the strong base frame that will support the entire structure. To prepare for assembly, small tabs and brackets are shaped and added, creating anchor points that hold the lantern steady during joining. As the artisan begins welding, tiny sparks flicker gently in the workshop. Each joint is fused with care, giving the structure both strength and a unique character that reflects the maker's hand. Additional fittings are crafted for mounting and connecting, ensuring that every part aligns with precision. Slowly, the lantern comes together, its geometry balanced and its details refined. Watching the process unfold piece by piece is a reminder of the patience, concentration, and artistry required.
The Dugard HD 2210 Heavy-Duty Vertical Machining Center is a high-precision, high-performance machine designed for efficient metal cutting and machining operations. It features a robust 2,200 mm bi-axis, 1,000 mm y-axis, and 900 mm z-axis traverse, providing a large working envelope suitable for various industrial applications. The machine's table measures 2,200 by 1,000 mm and supports a maximum load of 3,000 kilograms, ensuring stability during operations. The spindle operates within a speed range of 20 to 6,000 revolutions per minute, powered by a 15/18.5 kilowatts motor, and utilizes a Cat 50 taper for secure tool holding. The automatic tool changer is a bidirectional twin-arm system with 24 stations, expandable to 32, accommodating tools up to 300 mm in length and 15 kilograms in weight. Rapid traverse rates of 12 meters per minute in the X, Y, and Z axis, along with a maximum feed rate of 10 meters per minute, enable efficient material removal. The machine incorporates cooled ball screws for thermal stability, a spindle oil cooler, and full guarding for safety. Optional features include a 10,000 revolutions per minute spindle, a fourth axis, a swarf conveyor, and advanced probing systems, enhancing versatility and automation. Machining process in crankshaft manufacturing. The machining method involves material removal using cutting tools to achieve the desired crankshaft geometry. The typical machining steps include rough machining, precision machining, heat treatment, and finishing operations. Rough machining. In the rough machining stage, CNC lathes remove excess material from the raw forging or casting. Milling operations are performed to shape crankpins and main journals using CNC milling machines. This stage typically takes around 30 to 45 minutes per crankshaft. Precision machining. Precision machining includes grinding, drilling, and boring operations. Grinding is used to achieve final dimensional accuracy and a surface finish of raw less than 0.3 micrometers. Drilling and boring ensure precise oil hole and lubrication channel placements. The combined cycle time for grinding and drilling is approximately 60 to 90 minutes per crankshaft. Heat treatment and stress relief. To enhance durability, induction hardening is applied to specific areas such as journals and fillets, improving wear resistance. Tempering is performed to reduce brittleness while maintaining the required hardness, HRC 55 to 62. The heat treatment process, including cooling, generally takes 2 to 4 hours. Finishing operations. In the final stage, polishing achieves a mirror-like surface finish to reduce friction, while dynamic balancing ensures smooth engine operation. Finishing operations typically take 20 to 40 minutes per crankshaft. Machinery used. The crankshaft manufacturing industry relies on high-precision machinery, including CNC lathes for turning operations with tolerances of plus or minus 0.01 millimeters, CNC milling machines for precision shaping, and crankshaft grinders for micron-level journal finishing. Drilling machines ensure accurate oil hole positioning, while coordinate measuring machines, CMMs, verify dimensional accuracy. Materials used in crankshaft manufacturing. Crankshafts are subjected to high cyclic loads and must exhibit excellent fatigue strength, wear resistance, and toughness. Common materials used include forged steel, ductile iron, and billet steel. Forged steel, 42 CRM04, 4340, 1045, etc., is widely used due to its high strength and durability. Ductile iron, NGJS 702, NGJS 802, etc., is a cost-effective alternative suitable for low to medium-duty applications. Billet steel, EN24, 4130, etc., is employed for high-performance applications, offering excellent mechanical properties. Production output and efficiency. The total cycle time per crankshaft ranges between 3 to 6 hours, depending on design complexity. Medium to high volume manufacturing facilities produce 500 to 2,000 crankshafts per day. Advanced CNC machining reduces scrap rates to below 5%, and automation, including robotics and IoT-based monitoring systems, enhances productivity and quality control. Industry trends and future developments. The crankshaft manufacturing industry is continuously evolving with the adoption of advanced materials, such as titanium and composites, to reduce weight. The implementation of 5-axis machining enhances precision and reduces setup time. Sustainable manufacturing practices, including energy-efficient processes and waste reduction, are becoming industry priorities. The crankshaft is a crucial component in internal combustion engines, converting reciprocating motion into rotational motion. Given its vital role, the manufacturing of crankshafts requires precision engineering, high-strength materials, and advanced machining methods. The machining method is one of the most commonly used techniques in crankshaft manufacturing, ensuring high accuracy and efficiency. This article delves into the machining-based crankshaft manufacturing industry, discussing materials, processes, machinery, and production parameters.
BEXMYW demonstrates its multitasking ability. The sequence is engaging, showing how complex parts take shape step by step. The first stage uses a double tool holder for both rough and finish turning, eliminating tool indexing and saving cycle time. Grooving follows with another double holder, keeping operations efficient. Each cut feels purposeful, highlighting machine strength. Threading comes next, producing both V-threads and Acme threads in one setup. The Y-axis then enables milling of hexagonal shapes, followed by helical pocket machining. Off-center drilling and face engraving are added with smooth turret indexing. This flow of actions makes the process captivating to follow. Chamfering cleans the pocket edges, removing the need for deburring. Finally, spline cutting is achieved with a rigid hobbing cutter, supported on both ends, ensuring accuracy and surface quality. The conclusion shows remarkable integration of turning, milling, drilling, and hobbing. The process opens with a 63 mm milling cutter, advancing at 2,800 mm per minute. Next, a 40 mm indexable drill runs at 1,800 revolutions per minute, driving deep into the blank. A 16 mm Wodex EcoMill continues at 190 meters per minute, then again at 8,000 revolutions per minute, with 1,400 millimeters per minute feed. Smaller tools, 26 mm drill and 12 mm cutter, finish profiles at 1,600 millimeters per minute. The sequence feels intense and precise. Can you imagine how a single machine shapes both single-start and multi-start worms with flawless control? This setup is designed to handle both single-start and multi-start worms, along with double-lead right or left versions, offering wide flexibility in gearing production. The process opens with the rigid workpiece clamped securely in place. Rotational alignment ensures stability before the cutting head engages. Watching the tool bite into the metal highlights its robust design. With the spindle engaged, the machine drives the cutter along the helical path, carving the worm geometry layer by layer. At this stage, multiple starts can be programmed, enabling production of advanced forms. Double lead options are also supported, giving the component improved load distribution in gear assemblies. The smooth motion across the axis is striking to follow. Each pass removes material efficiently until the full worm profile emerges. The final result is a worm ready for transmission systems, produced with reliability and repeatability. Such consistency inspires confidence in large-scale applications. By integrating both standard and advanced cutting capabilities, the system delivers components that meet demanding industrial requirements. Every rotation reinforces the machine's strength. Powerful cutting dynamics open the scene, highlighting rough turning with a Sandvik Tapdo holder. The Corway CNMG 432 LP3515 insert engages the workpiece, removing material with strength and consistency. Coolant through YG1 Dream Drill follows, maintaining chip evacuation and dimensional control. The coordination looks truly impressive. Engines in aerospace demand components built with strength, geometry, and reliability. On this machining floor, the WFL aerospace machine shows how complex parts reach their form through multiple coordinated stages. The sheer control on display sparks admiration immediately. The sequence opens with raw material held firmly in the spindle, prepared for milling and turning operations. Large cutting tools remove excess stock, shaping the exterior into a recognizable profile. Each pass steadily defines surfaces, preparing the blank for more demanding cuts. It feels powerful to see steel reshaped so quickly. Drilling operations follow, supported by through coolant supply to manage heat and prolong tool performance. Holes of various depths and diameters are executed, vital for connections and mounting. Afterward, fine finishing tools glide across surfaces, ensuring smoothness and dimensional stability. The finish at this stage looks remarkably clean. Next, boring heads enter, enlarging internal diameters with consistent accuracy. Grooves and channels are machined into the workpiece, ensuring compatibility with aerospace assemblies. Tool changes are performed automatically, keeping the process efficient and uninterrupted. Automation here feels seamless and dynamic. Finally, the completed aerospace component leaves the spindle, meeting the exacting standards required for flight. Every cut bore and drilled feature contributes to performance and safety. The outcome highlights how technology pushes boundaries in manufacturing. Strong engineering meets motion, as CNC mill-turned machining demonstrates how bar stock transforms into precise forms. The energy of cutting sparks real excitement. Holes are drilled using solid drills, ensuring depth and stability. Tool holders maintain rigid clamping, minimizing vibration during machining. Then rotation begins for turning operations that define outer contours. Milling heads then engage, cutting slots, flats, and complex geometries. Each transition between turning and milling feels incredibly fluid. Engines gain new life when a V8 block undergoes honing on the Rotary H75 CNC machine. The cycle opens with rigid clamping, securing the heavy block. Abrasive stones then extend, refining cylinder walls with uniform contact. Each stroke improves roundness and surface finish. The pace is intense, yet the outcome feels flawless. Chips scatter rapidly when the YCM NXV1020 combines its stability with EdgeCam Waveform's dynamic milling path. The first step engages the spindle at programmed speed, initiating stable cutting conditions for the cycle ahead. Once rotation is established, the end mill makes contact, following optimized tool paths. Waveform technology keeps the cutter in constant engagement with the material, minimizing stress while enabling deeper cuts. The scattering of chips reflects efficiency and control in motion. Progress continues as the cutter sweeps across surfaces, removing layers with consistent feed. Corners and pockets are machined with steady angles, avoiding sudden tool load increases. The controlled feed rate ensures both productivity and tool longevity. As passes advance, the machine maintains reliable spindle performance with smooth chip evacuation. Every transition reveals the strength of both programming and hardware. The final workpiece emerges with refined geometry, proving how intelligent software and robust construction achieve outstanding results. Raw billet aluminum weighing nearly 500 pounds is shaped into engine blocks and cylinder heads. CAD design defines specifications before machining begins. Heat treatment strengthens the material, followed by honing for accurate bores. Sleeves are installed to reinforce durability. The engineering intensity feels remarkable at every stage. Final inspection ensures components meet the high standards demanded in racing. The PFM 137 portal milling machine handles rail machining with striking force and control. A table length of up to 25,000 millimeters provides space for massive workpieces. The 137 kilowatt spindle engages with SK60 tooling for heavy-duty operations. Automatic change to an angle head expands versatility. Watching each movement reinforces how scale and accuracy dominate this process. Energy flows through each step of drill bit production. First, rods are cut into measured lengths. Then, forging shapes the taper shank. Heat treatment builds hardness. Flutes are ground for chip removal. Finally, sharp edges highlight remarkable strength. Strength defines screw machining for injection molding. Steel bars are mounted on CNC lathes where turning gradually defines the screw body. Specialized tools carve spiral threads in continuous flow. Finishing smooths the surfaces, and inspection validates quality. Each stage builds on the last, leaving a strong impression. Vertical turning on the FVL 1600 VTC plus CY shows remarkable capability. Heavy-duty cuts shape the exterior with strength. Fine turning follows, refining dimensions with steady flow. Face milling broadens surfaces, while drilling and rigid tapping complete structural features. Optional grinding enhances finish, leaving the part strong and reliable. Vertical turning on the FVL 1600 VTC plus CY shows remarkable capability. Heavy-duty cuts shape the exterior with strength. Fine turning follows, refining dimensions with steady flow. Face milling broadens surfaces, while drilling and rigid tapping complete structural features, leaving the part strong and reliable. A 26-ton housing requires drilling 4 bores, 220 millimeters wide, and 1,500 millimeters deep. First, drilling reaches halfway with cooling plates. Then rotation flips the housing for continuation. Finally, HSS inserts drive-through to breakthrough. High-performance turning defines the LB3000EX, tackling demanding parts with confidence. The machine supports a maximum diameter of 410 millimeters and a length of 500 millimeters. Its JIS A26 spindle nose handles speeds from 45 to 5,000 minutes, Rapid traverse of 25/30ths of a meter per minute accelerates workflow. With 22/15ths of a kilowatt spindle power, components are shaped with strength. The balance of speed and stability feels outstanding. The Wortmann 550-7 CNC flat and angle machine accelerates steel processing with gripper speeds of 1.2 meters per second. Flat profiles up to 500 millimeters and angle lines up to 200 millimeters are handled efficiently. Operations include punching, shearing up to 45 degrees, drilling, countersinking, and thread tapping. Automatic tool changes and length measurement enhance workflow. Nibbling holes and adding stiffeners increase functionality. The sturdy drill spindle and modular construction maintain stability while delivering speed. The flow of operations showcases the machine's power and efficiency. The CNC punching machine begins by aligning the Saint 37 material up to 46 millimeters diameter and 25 millimeters thickness. 3 punches, including marking, operate sequentially with automatic transitions. The process is efficient and precise. The HACO Q3 turret punching machine positions clamps on the 2000 by 1000 500 millimeter sheet, readying it for precise marking. Automatic tool changers engage, selecting from the punching head options, including 22 or 30-ton servo hydraulic heads, pincher, extrusion, forming, offset, rib, and shear wheels. The machine begins punching, producing clean holes and forms with minimal noise. The rotation axis allows all tools to operate efficiently across the sheet. As the process continues, repositioning cylinders adjust the sheet, enabling complex patterns. Operators can monitor the intuitive TPC69T graphics controller, managing high-speed processing and intricate sequences. Observing the machine handle these varied tasks demonstrates its reliability and impressive versatility. A 6 millimeters thick carbon steel sheet is clamped firmly, ready for precise CNCOXICORTE cutting. The torch moves along programmed paths, shaping the metal into precise contours. Operators adjust cutting speed and oxygen flow to optimize results. As the process progresses, edges become clean and smooth, reflecting the machine's efficiency. The system allows complex designs to be executed without errors. Observing the metal gradually take the desired form highlights both the machine's capabilities and the skill of the team managing the operation.
Thermic lancing is a highly effective method for cutting through solid steel counterweights, utilizing extreme heat to melt and oxidize metal rapidly. A thermic lance, also known as an oxygen lance, consists of a hollow steel tube filled with alloyed steel rods. When ignited and supplied with pure oxygen, the lance burns at temperatures exceeding 4,000 degrees Celsius, 7,200 degrees Fahrenheit, easily cutting through thick and dense materials like steel counterweights. The process begins with preheating the tip of the thermic lance using an oxyacetylene torch. Once sufficiently heated, oxygen is introduced, triggering an exothermic reaction that generates intense heat. As the operator moves the lance across the counterweight, the metal liquefies and oxidizes, forming slag that drips away, leaving a precise cut. Thermic lancing offers several advantages over conventional cutting methods, such as oxy-fuel or plasma cutting, particularly for thick, heavy-duty steel components. It is effective even in submerged or challenging environments, making it ideal for demolition, decommissioning, and salvage operations. However, the process requires strict safety precautions due to the extreme temperatures and molten slag. Operators must wear heat-resistant protective gear, maintain proper ventilation, and follow fire safety protocols. Once heated, The billets are fed into forging presses, where they are shaped into spherical forms. The plant uses two forging methods: upsetting process for larger balls, Phi 100 mm to Phi 120 mm, conventional forging for medium-sized balls, Phi 60 mm to Phi 90 mm. After forging, the balls are transferred to a trimming press, where excess material is removed to achieve the desired shape and weight. Next, the forged balls undergo heat treatment, hardening, to enhance their mechanical properties, increasing their strength and wear resistance. Finally, the hardened balls are inspected, sorted, and packaged according to size and quality standards. The finished steel balls are then ready for delivery and industrial use. Production process of shell casings. The production of shell casings involves multiple stages, including forging, machining, and final shaping. Each step ensures that the casings meet high precision and durability standards. Forging line for shell casings. The process begins with automatic loading of steel bars into the production line. The bars are heated using an induction heating system with a power capacity of 1,450 kilowatts and a frequency of 500 Hz. Once heated to the required temperature, the bars are cut to size using a hydraulic press shear, capable of cutting steel rods up to Phi 130 mm. The cut pieces then enter the UMUCO hydraulic forging machine, where they undergo two key steps: upsetting and piercing using 630-ton force with a ram stroke of 1,250 mm. Calibrating and drawing with 200-ton force, where rollers and rings refine the forged casings to the required shape. After forging, a robotic handler arranges the hot casings into pallets for normalization, a process that relieves internal stresses and improves structural integrity. Machining line for shell casings. Once normalized, the forged casings move to precision machining. The first step involves turning on a hydrocopy lathe, a high-productivity machine that shapes the casings. Next, a final turning lathe performs additional machining for precise dimensions and surface finish. Automated technological module for shell casing compression. This stage ensures the final shape and structural integrity of the casings. The process starts with an automated loading system that feeds the casings into an induction heating system, operating at 375 kilowatts and 1,000 Hz. After heating, the casings pass through a vibrational forging machine, usine de Wecker, where they undergo controlled compression. Two manipulators assist in handling and positioning the casings throughout this process. The manufacturing of the all-thermoplastic upper shell of the MFFD involved advanced automation and innovative welding techniques. Key production steps included in situ consolidation, compression molding, and high-precision ultrasonic welding. The process began with the in situ consolidated layup of the fuselage skin, where 53 kilometers of thermoplastic tape was placed layer by layer. Airnova contributed by producing 44 compression-molded Z-stringers, which were prefixed to the fuselage skin using a robot-based ultrasonic spot welding technique at intervals of 500 millimeters. This was followed by the world's first fully automated, continuous ultrasonic welding of all 44 stringers, ensuring a strong and durable bond. Premium Aerotech was responsible for the production of 24 compression-molded C-frames and additional structural components. Automated integration of the frames was achieved using resistance welding, totaling approximately 300 welds. Additionally, 12 frame couplings and 158 cleats were incorporated through cobot-based resistance welding, ensuring a robust connection between structural elements. The welding process utilized DLR-developed end effectors and a specialized weld bridge to align and join components with high precision. Ultrasonic welding generated high-frequency vibrations to heat and bond the stringers and skin efficiently, while resistance welding enabled rapid frame and cleat integration. This dustless and efficient process significantly reduced production time, supporting the goal of a lightweight, low-footprint fuselage for next-generation aviation. Spot welding robots in the automotive industry use high-powered electrodes to join metal parts by applying pressure and an electric current. The process involves the robot positioning the welding gun at precise points on the car body, clamping the metal together, and delivering a short, intense electrical pulse to create a weld. These robots work with high speed and accuracy, ensuring consistent weld quality. Integrated sensors and vision systems optimize performance, while automation increases efficiency, reduces labor costs, and enhances vehicle structural integrity in modern manufacturing. BMW's rollover safety crash tests take place at its specialized facility, which evaluates vehicles equipped with rollover sensors. Although not required by the National Highway Traffic Safety Administration or any government, these tests align with BMW's safety philosophy. The facility conducts 3 primary tests: the corkscrew test, the sandpit test, and the embankment test. The corkscrew test simulates an induced rollover by forcing a vehicle into a barrier. The sandpit test replicates scenarios where a vehicle slides sideways off the road. The embankment test mimics a vehicle rolling down a steep incline or ditch. The BMW X6, featuring a low center of gravity and high-strength steel reinforcements, underwent rigorous testing. Its advanced rollover sensor system detects angular acceleration and impact types to trigger safety mechanisms, ensuring enhanced passenger protection. The tire pyrolysis batch plant by KGN Industries is designed for an efficient and pollution-free conversion of waste tires into valuable byproducts. The process begins with the mechanical loading of tire bales into the reactor using a mobile crane. This method ensures efficiency and safety while preparing the tires for pyrolysis. After the pyrolysis process, carbon black removal takes place once the reactor temperature drops below 50 degrees Celsius. The carbon black is extracted mechanically and packed into jumbo bags, preventing spillage and ensuring clean handling. These bags are then transported smoothly within the facility for further processing or sale. For the steel extraction, water is sprayed on the material before removal, preventing dust formation. The steel is then mechanically removed and stored in a separate area designated for metal storage. Additionally, the plant features dedicated storage spaces for both carbon black and steel, ensuring organized handling and pollution-free operations. The plant yields approximately 40% oil, 38% carbon black powder, and 15% steel, making it an efficient and sustainable solution for tire waste management. The furnace is fired using liquid fuel and pyrogas, creating an oxygen-free environment where the tires break down into oil, carbon black powder, and steel through thermal decomposition. This batch processing system can handle 10 tons of tires per day, following a structured workflow that ensures minimal environmental impact while maximizing resource recovery. The cutting process begins when the operator starts the engine. The diamond blade, designed with embedded industrial diamonds, grinds through the concrete rather than slicing like a traditional saw. Water is often used during cutting to cool the blade, reduce dust, and prolong blade life. Some models feature vacuum attachments for dry cutting, minimizing dust exposure. Husqvarna concrete cutters typically have depth control adjustments, allowing users to set the blade at the right cutting depth. The machine moves along the cut line, guided manually or with self-propelled mechanisms in advanced models. For precision cutting, some models also include laser guides. Safety features such as kickback reduction, blade guards, and ergonomic handles help operators maintain control. The Husqvarna concrete cutter works by using a high-powered motor to rotate a diamond blade at high speeds, allowing it to cut through concrete, asphalt, and other tough materials. These cutters come in different types, including walk-behind saws, handheld saws, and wall saws, each designed for specific cutting tasks.